Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, and welcome back to the course Organic Electronic Devices. In our last lecture, we discussed polymer thermoelectric devices, and we introduced you to the motivation behind why we'd want to use thermoelectric devices, what some of the inorganic materials used today are, why we might want to use polymer thermoelectric materials, and really kind of motivated how polymer thermoelectric materials could make a significant impact in thermoelectric devices in the grand scheme of things. Okay. Today what I'd like to do is move beyond what we've seen before and go into the state of the art with respect to polymer thermoelectric devices and polymer thermoelectric materials. Okay. And hopefully understanding what the state of the art in these materials are will help us design better materials with respect to polymer thermoelectrics and really understand how we can play and tune conditions such that we have this high performance and higher figures of merit. Okay? So what we'll do is we'll discuss what initial polymers were used in terms of thermoelectric materials and discuss why some of the strategies worked well and what some of the strategies needed to be improved to reach the state of the art we have today. We'll then move on to talk about PEDOT PSS, a material that we've seen numerous times, okay, both in OLEDs and OPVs as the whole conducting layer, and how PEDOT PSS is really pushing the front in terms of the P-type leg of polymer thermoelectric devices as well. Okay? And then we'll touch on how we can use both polymers and inorganic nanoparticles, okay, and the composite of those two materials to make high-performance thermoelectric devices as well. Okay? So we'll go into hybrid systems. So by the end of the lecture today, what we'll hope to see is that we'll be able to name at least 3 materials that have been of high utility, we'll say, in polymer thermoelectric devices. Okay? And really what we hope we get out of this is that we can explain why doping matters so much in polymer thermoelectrics. Okay? We haven't talked a whole lot about doping throughout the other device applications because we've been really keen on looking at the semiconducting properties. Now we want to push those semiconducting properties to the limit and figure out how we can maximize that electrical conductivity so that we can maximize ZT. And really doping and using molecular dopants is a very powerful way to do that. Okay? And then the last thing we like to be able to do is justify why one might move to inorganic organic, so inorganic polymer, okay, hybrid thermoelectric systems. And there's some very good reasons why one would want to do that, and we'll touch on those with 2 example cases. So let's get started. Okay. And before we move into polymers, I'd first like to give a feel for the order of magnitude of materials we're working with here. Okay. So here we have a plot of ZT versus temperature for a whole suite of inorganic systems. Okay, and this goes anywhere from very, very low temperature, so 100 K, all the way up to 1400 Kelvin. And really, I'll remind you that for our polymers, we're going to really want to work in this very low temperature range, so almost absolute zero, up to about 500 K. At that point, our polymers, if they haven't started to flow or melt at that temperature, right, they're definitely going to start to think about degrading between the carbon-carbon bonds. Okay? So we're going to be operating in this low temperature regime. So we can see in this low temperature regime, really, the figure of merit ZT for these materials is somewhere, and these are the best inorganic materials we can find, for these materials is somewhere between 0.8 and 1 is what ZT maxes out to be. Okay? So with that in mind, when we look at our polymer thermoelectric materials and we look at the ZT values that we can calculate for our polymer materials, and we measure our ZT values experimentally for our polymer thermoelectric devices, we really need to keep the benchmark of the best materials in the world is between 0.8 and 1. Okay? And when polymer thermoelectric materials started out, this is roughly in the early 90s. Okay? The first material that was really looked at in depth was polyacetylene, or PA. Okay? And here we have polyacetylene. We can see that we haven't doped it, but if you look at the electrical conductivity of polyacetylene, it's somewhere on the order of 6,000 inverse ohms, inverse centimeters. Its Seebeck coefficient is around 21 microvolts per Kelvin, and that gave it a power factor of somewhere on the order of 10 to the negative fourth watts per meter Kelvin squared. Okay. If you look at polyaniline, okay, you can see that it has lower performance values, so it's not studied quite as much. But those are two materials that kind of were at the outset of this polymer thermoelectrics idea. Okay. Now, one way you could increase the conductivity when we talked about inorganic systems is to dope it, right? And polymer systems have a similar terminology and a somewhat similar mechanism in the fact that they can also be doped, but they're doped with molecules instead of individual atoms. Okay. And if we dope polyacetylene, okay, and the first case here was to dope it with FeCl4, okay, we can see the conductivity goes up, the Seebeck coefficient remains roughly the same, okay, and that gives us a higher power factor. Okay. And you can see, depending on how you dope it and who's performing the task, that it varies a little bit, but it's on the order, again, of 10 to the negative fourth watts per meter Kelvin squared. Okay. So FeCl4 is a decent dopant. It increased the conductivity a little bit. It does have some problems with respect to long-term stability. So what people move to is doping with iodine. Okay. And when people dope polyacetylene with iodine, you can see that the conductivity shoots way up, all the way up to 50,000, so almost an order of magnitude higher, right? The Seebeck coefficient between the very first entry in the table and the one in the bottom is exactly the same at 20. And that puts it a power factor at 10 to the negative third watts per meter Kelvin squared. Okay? So now we have this relatively high power factor. Okay, remember if we multiply that by 298, because all of these operate roughly around room temperature, and then divide by the thermal conductivity, and the thermal conductivity for polymers is somewhere on the order of 0.1 to 0.2, then we can back out ZT. But let's just look at this power factor right now. We're on the order of 10 to the minus third. That's extremely high. Okay, this looks great. So the big question becomes, why don't we just have a bunch of polyacetylene doped with iodine thermoelectric modules in place today? These are very high values. Okay? And the answer is because they're not stable. Okay, the iodine comes in a vapor form. It can easily be pulled out of the polymer. It'll evaporate over time and it'll become undoped. And it'll reduce back down to a very low power factor value. Okay, so while we need to dope and we need to think about how to dope, we also need to be careful and make sure that our dopants aren't transient with respect to time. That is, both the device won't break down and our dopant won't leave the device. Okay. And the best way to dope that people have found to date without having a transient material is to have the dopant be polymeric as well. Okay? So now we're going to have our PEDOT PSS. So remember, PEDOT PSS is this polyethylene dioxythiophene, right? And it's doped with polystyrene sulfonate. Okay? And people have used PEDOT PSS in quite a number of applications, including thermoelectrics, and they've used pristine PEDOT PSS as well. It performs fairly well. It has a nice figure of merit. Okay? But in a recent result, what people have done is actually oxidize it further. And to do that, they've used an organic compound that's based with an iron atom in the center. Okay? This iron tosylate. And they've used this to oxidize the PEDOT PSS beyond what it is straight out of the bottle. Okay? Now when you do this, you can actually look at how the device performance changes as a function of oxidation level. Okay? And if we look here in the closed triangles, okay, we can see that initially the Seebeck coefficient is relatively high, and then it begins to decrease, okay, begins to decrease with increasing oxidation level. Okay, it goes somewhere from 800 down to roughly 100. Okay. The conductivity, on the other hand, shoots up from 10 to the negative 3 Siemens per centimeter all the way up to over 100. Okay. And because of these two competing effects, just like we see a lot of times in the inorganic systems, okay, we see a maximum in S squared sigma. Okay, and here it occurs at an oxidation level of around 22.5%. Okay, so now the question becomes, how does this impact ZT? Okay, well, it turns out that this oxidation doesn't necessarily affect the thermal conductivity. So then the plot of ZT versus oxidation percent looks very similar to the numerator of the ZT value, so the power factor. Okay? And what this tells us that at room temperature, we see that the ZT value for this doped PEDOT PSS is roughly 0.25, right? And that's not bad, right? Because remember, the best performing inorganic materials at room temperature are somewhere on the order of 0.8 to 1. So we're a quarter of the way there through a simple doping strategy. Okay. And because of this, now we can think that if we're a quarter of the way there, we can really go back to what we talked about in the last lecture and think about how much do all the materials cost and which way is the more efficient way to produce these materials in the large scale. Okay? So that's great. Okay? However, we can take it one step farther. Okay? And if we take it one step farther, we can even increase the thermoelectric performance of PEDOT PSS even more. Okay? And the way we do that is by removing some of the PSS. Now you'll remember PSS is that polystyrene sulfonate. Okay? It's electrically insulating. The reason we use it is because we polymerize EDOT to make PEDOT in the presence of polystyrene sulfonate. Okay? But once we've polymerized the EDOT, have it soluble in solution and make our thin film, the PSS is just kind of in the thin film, not doing a whole lot for charge transport. So what people have been able to do is actually dip the thin film in ethylene glycol, or EG, and that's what EG treatment means, okay, for various amounts of times to remove some of that PSS. Okay? And you can see when they do that the Seebeck coefficient of PEDOT PSS increases. Okay? The conductivity increases substantially. Okay? The thermal conductivity doesn't really change. It stays at roughly 0.28. So that tells us that our ZT will actually increase in the same manner as the power factor increases. Okay? And when that happens, we see that we can get up to 0.42 ZT at room temperature. So now we've almost doubled what we did last time, and we're basically halfway to being where the best inorganic systems, which have been studied for much longer than polymer systems, are. Okay? So now we're starting to really be able to play an optimization of PEDOT PSS could be an amazing way forward for polymer thermoelectric materials. Okay? Now you'll recall our thermoelectric devices have two legs. They have both a P-type leg and an N-type leg, right? And our P-type leg might very well be PEDOT PSS, but you'll recall from our organic photovoltaics and our organic light-emitting diodes, okay, that PEDOT PSS is hole selective, right? It really likes to be P-type. But we need an N-type leg as well, right? So discovering new materials, new polymers that are preferentially electron transporters is also very important in terms of thermoelectric materials and devices. Okay? And that work has just started to get ongoing, okay, over the last 2 to 3 years. And one of the initial high-performance materials that have been found, okay, is this bulky conjugated polymer here, where we have this electron donor electron acceptor structure that we might remember from our low band gap polymer discussions, right? Okay. And it turns out that if you have this material and you add in dopants, okay, either DMBI, the upper one, or DPBI, the lower one, okay, and the difference between these is either the methyl group or the phenyl group on these materials, okay, we actually see that with adding dopants, we can increase the conductivity of this material. And what we see is that at relatively low molecular dopant concentrations, between 5 and 25%, we actually see a 3 order of magnitude increase in the conductivity of these materials. Okay? You'll note that the conductivity is 10 to the minus 3 here at the maximum Siemens per centimeter. Okay? So this is roughly 6 orders of magnitude less than what we were seeing in the PEDOT PSS, but you have to remember this is a much earlier generation of material, much less well studied than PEDOT PSS. So hopefully we'll be able to take it up to a higher level soon. But the interesting thing is that the Seebeck coefficient is very, very high. Okay? It's roughly 850. And you'll note that when we have an N-type material, the Seebeck coefficient is negative, and when we have a P-type material, the Seebeck coefficient is positive. And that's by definition, that's by nomenclature. But remember, S is always squared in the power factor in the ZT terms, so the sign doesn't matter in terms of our device performance. It just lets us know whether it's P-type or N-type. But here we see that it's roughly 850, so then we get power factors now that are on the order of microwatts per meter Kelvin squared. Okay? So we're at, for N-type materials, at that level that we were for P-type materials roughly 10 years ago. So we're getting there. It'll just take more research, more materials design on how to get to the higher level. And in fact, an exciting thing to do is to take a material and instead of doping it with external dopants, is to have internal dopants. So here we have our N-type polymer, but now we're going to dope it with a material that's actually covalently bound to it. Okay? So now we have an intramolecular dopant. Okay? And it turns out how you dope these things and what the length of this the spacer group, how many CH2 groups I put between the main chain, okay, and the side chain, it matters in terms of its thermoelectric response. And what we see is that if we have a spacer length of 2, 4, or 6, the Seebeck coefficient stays relatively flat around -200, but the electrical conductivity shoots up, okay, and it approaches 1 Siemens per centimeter. Okay? And if that's the case, then we can see that our power factor is roughly 1 microwatt per meter Kelvin squared. And really, that's one of the highest performing devices for N-type materials that has ever been seen for organic thermoelectric materials. Okay? So we're getting there. N-type is not as well developed as P-type materials, but it's coming closer and closer each day. And really, the design and synthesis and implementation of these new materials will help drive thermoelectric devices, and polymer thermoelectric devices in particular, to the next level. Well, the last thing we'll discuss, okay, is the idea of hybrid inorganic polymer systems. Okay? And we saw on the first slide that bismuth telluride was one of the highest performing P-type inorganic materials. So maybe rational strategy would be to combine bismuth telluride, which performs well in organic material, PEDOT PSS, one of the highest performing polymer thermoelectric materials for P-types, and combine them to see if we can get some kind of synergy. Okay? And the answer is yes. And people have done this, and they can make nice sheets of bismuth telluride right here that are roughly 500 nanometers in width. And when they do this, what they see is as they load more bismuth telluride nanosheets in there, right, they see an increase and then a leveling off of the electrical conductivity. You can see this is very high, roughly 1200 Siemens per centimeter. And we also see that the Seebeck coefficient goes ahead and it increases as well, but it stays within this modest range of 10 to 18, what we're used to seeing for polymer semiconductors. So what happens is that the power factor goes all the way high as 35 microwatts per meter Kelvin squared. Okay? So now we're getting the benefits of both the inorganic material and the polymer material while retaining the thermal conductivity of a polymer, which is very, very low, which is great for ZT, right? Because we want to keep that thermal gradient high between T hot and T cold. Okay? We can also think about doing this with PEDOT PSS and tellurium. So what happened here is actually tellurium nanowires were formed in the presence of PEDOT PSS to form these nice tellurium nanowires that have a sheet of PEDOT PSS around them. Okay? And now you have an inorganic nanorod with a layer of polymer wrapped around it. Okay? And the question is, does this perform the same as the polymer, the same as the nanorod, or better or worse than either one? And the answer is better, right? So here we have our PEDOT PSS pure, its conductivity is roughly 1. The T nanowires are roughly an order of magnitude lower, but then the PEDOT PSS with tellurium jumps up by a factor of 20. Okay? We'll see that the Seebeck coefficient increases drastically, which leads us to a ZT of around 0.1. Okay? So this isn't quite as high as pristine PEDOT, okay? At least modified PEDOT PSS. Okay? But this is pristine PEDOT, wrapped with tellurium around it. Okay? So the idea then is can we now take our PEDOT PSS with tellurium nanowires around it and do those same chemical modifications we saw earlier to get that ZT of 0.42, can we do those same chemical treatments to increase this nanorod system? Okay? Because this material right here is just as solution processable, just as cheap as PEDOT PSS itself. Okay? And really moving forward, inorganic polymer hybrids might end up being the best of both worlds. Okay? So with that, what I've hoped to show you today is the fact that polymer thermoelectric materials can really play in the low temperature regime with respect to both device performance and always with this underlying thought of cost of fabrication and the cost of materials that go into the thermoelectric devices. Okay? And then not only can we use polymers, but if we design inorganic nanoparticles or nanorods the appropriate way, polymer inorganic composites could play a huge role in order to have a synergy that goes beyond the thermoelectric performance of either one of the individual components. Okay? So the prospect for thermoelectric materials and polymer-based thermoelectric devices is very bright. We need to discover new materials. We need to work on N-type materials. But the groundwork's there, the theory's there, and the limitations associated with inorganic materials aren't quite as obvious. So there could be a great way to move forward with these new materials and these new devices. In our next lecture, we'll review what we've talked about throughout the course of this series. Okay? And we'll talk about how all of these concepts pull back together and really lets us go from molecules to modules in organic electronic devices. With that, I thank you for your attention, and I look forward to seeing you in the next installment of Organic Electronic Devices.